All right. So last time we discussed the periodic table, the periods and groups. So today we'll talk about the other parameters. Now, we did the history of periodic table, what all efforts had been made by different scientists to classify elements, and
Excuse
finally
me,
we
sir.
came up. Yes.
Sir, I was not attending your previous class, so can you just recap that what you have learned yesterday, what you have taught yesterday?
Okay. It was I think last week. Okay. So basically, we did history, and that history is okay. That the history is still, understandable if you read from the textbook. But the main part is that the modern periodic table is important. We discussed the evolution of the modern periodic table, and also we said that we also discussed the basis of classification. That is, we said that the parameter or the premise which has been used to classify elements in the modern periodic table is the atomic numbers. So the atomic numbers of the elements are telling us how we should classify them, because if we know the atomic number of an element, we can write its electronic configuration, and then we can classify the elements based on the number of valence electrons. Valence electrons are electrons which are present in the last shell of an element. So if I say that the valence shell has one electron, then all those elements which have only one valence electron will be placed in the same category, and they all will be placed in the same group. So a group, what is a group? A group in the modern periodic table, a group in the modern periodic table has elements. A group in the modern periodic table has elements having similar properties. This is a very important question for the exam. You can ask you what are the common characteristics of elements present in the same group. So you can see that a group has elements having similar properties. Similar properties. Every element, every element in a particular group, every element in a particular group has the same number of has the same number of valence electrons. Every element in the particular group has the same number of valence electrons. This is extremely important. So if I say that, what about group 1? Then I say that group 1 has, or every element in group 1, each element in group 1 has one valence electron. That means only one electron is present in the last shell. Last shell is also called valence shell. E minus means electron. Similarly, each element, we will do some questions later, so these points can help you there. Each element in group 2 has two valence electrons. Each element, each element in group 13 has three valence electrons. Each element in group 14 has four valence electrons. Likewise, you should remember all these things. Okay, so we must know the valence electrons present in every group. So I gave this points. This is extremely important. Now, the basic arrangement of modern periodic table should be known to you. So, if I'm talking about this one, hydrogen, here I have, let's say, helium. Then here I have lithium, beryllium. Here I have boron, carbon, nitrogen, oxygen, fluorine, and neon. This arrangement should be known to you, but I'm showing now. Questions are based on this arrangement. So this arrangement must be known to you. So this is the arrangement. So I can say that this this is first period. Each horizontal row is called a period. So from hydrogen till helium is one period. Second period is from lithium till neon. Third period is from sodium till argon. And fourth period starts from potassium. So right here, period one starts with hydrogen and ends at helium. Period two, period, period two starts with lithium and ends in neon. Period three, you must know the starting and ending elements. Starts with sodium and ends in argon. Ar is argon. Period four starts with potassium and ends with krypton. Kr is krypton. So I will write here. So this is how it is. So if they ask you which is the first element of period 3, so then immediately you should be able to say that the first element of period 3 is sodium and so on. So that is why I wrote this. Now, all these elements which are inert gases, that is helium, neon, argon, krypton, xenon, radon, all these inert gases are in group 18. Group 18. So what is group 18? As you can see here, each element in group 18 has 8 valence electrons, except helium, which has 2 valence electrons. So all the inert gases are in group 18. So they can ask you which group in the periodic table has all the inert gases. So we'll say that group 18 has all the inert gases. Inert gases are also called noble gases. Okay. Now we will understand certain terms, and that is why I wrote these elements in this specific format because this is the arrangement. Right? So as you go from left to right, so what is left to right? A period. A period is, or you can say like this: if we move across a period, if we move across a period, it means that we are moving from left to right. This is important. If we move across a period, it means that we are moving from left to right. If we move down a group, if we move down a group, it means that it means that we are moving from top to bottom. These are the important terms that we must know. So if I'm saying that I'm moving down the group, that means I'm moving like this, like this, like this. So if I'm moving down the group, that means along a specific vertical column, I'm moving from top to bottom. If I say that I'm moving across a period, that means I'm traveling like this, that is left to right. This is a movement if I'm saying that I'm traveling across the period. That is along the same horizontal row. So across the period means left to right, and down the group means from top to bottom in the same vertical column. So these are the terms that you have to know. Now, okay. Now let's understand certain terms. Certain terms. First one, size. Let's give a heading first. First, atomic size, also called atomic radius. So let's understand this. Now see, if I'm talking about size, so size will depend on factors like number of shells and the nuclear charge. So let's understand these things. If I'm having an element, this is the nucleus, let's say. Around the nucleus I have shells, okay? I have shells, and the electrons are present in the shells. The nucleus is positively charged because it has protons and neutrons. The neutrons are neutral. So the charge on the nucleus is only because of the protons which are present. So the nucleus is positively charged, and the electrons which are present in the shells are negatively charged. So electrons are negatively charged and the nucleus is positively charged. Now, there exists a force of attraction between the nucleus and the electrons because of opposite charges. So the nucleus and the electrons are attracted towards each other. So the nuclear charge refers to the charge because of the protons present in the nucleus. So if I say nuclear charge, that means I'm talking about the protons which are present inside the nucleus. Whatever charge is present, whatever charge is being talked about, refers to the protons because all the protons are positively charged. That means the nuclear pull or the nuclear charge refers to the attraction between the nucleus and the electrons. So if I say that the nuclear pull is more, if I say that the nuclear pull is more, that means the electrons are effectively attracted towards the nucleus. So if the nuclear pull is more, that means electrons are more effectively attracted towards the nucleus. And if the nuclear pull is not that great, that means the electrons are not that strongly attracted by the nucleus. So if I increase the number of shells, let's say if I have many shells, definitely the size will go up because size refers to the radius. How is the radius measured? The radius is measured from the center of the nucleus to the extreme shell, that is the valence shell. Just like the radius of a sphere or the radius of a circle in mathematics. More the radius, larger is the size. So if I go on increasing the number of shells, then definitely the size will keep increasing. So remember that the number of shells will determine the size or the atomic radius. But if I say that the number of shells is same, let's say there are two different elements having the same number of shells. Let's say like this, I have two shells. But the charges are different because if the elements are different, the number of protons will also be different. Every element has a unique number of protons. That means the number of protons and the number of electrons will be different, irrespective of the fact that the number of shells is the same. So the number of shells is same, but the number of protons and the number of electrons are different in the two elements. Then how will we determine the size? So then we have to see the nuclear pull. This nuclear pull. So if the charge in the nucleus is of greater magnitude, that means if the nuclear pull is high, definitely the size is going to be small because then the nucleus will effectively pull the electrons towards itself. If the nucleus is able to pull the electrons effectively towards itself, that means the pull is more. If the nuclear pull is more as a result of the nuclear charge being more, I can say that the size of the atom will shrink. So if the nuclear pull is more, that means it is pulling the electrons towards itself. Because of this pulling, definitely the size of the atom will be smaller than expected. But if the nuclear charge is smaller in magnitude, then the size will be larger than expected. So it depends on the nuclear pull, and if the number of shells is the same, then we will see the nuclear pull. How do we see the nuclear pull? We count the number of protons present. More the number of protons, more is the nuclear pull, and hence smaller is the size. So I can say that if I am moving from left to right, so on moving across the period, on moving across a period, the size on moving across a period, the size decreases the size decreases from left to right. On moving across a period, the size decreases from left to right because, or as, the number of shells remains the same. As the number of shells remains the same, but the nuclear charge increases. But the nuclear charge increases. So what is happening? Let's take the example of this particular period. Let's say I'm talking about period number 3. Let's say that I'm talking about period number 3. So what is happening in period number 3? The first element is sodium. Let's say I'm traveling from sodium till chlorine. If I'm traveling or moving from sodium till chlorine, I'll write down the electronic configuration. So electronic configuration of sodium is this 2, 8, 1. And the electronic configuration of chlorine is
So,
this 2, 8, 7.
so can you please give some this sums regarding this group and period?
Yes, I'll give questions. I'll give.
Okay.
So 2, 8, 1 is the electronic configuration of sodium, and 2, 8, 7 is the electronic configuration of chlorine. I can say that in sodium there are 3 shells. There are 3 shells. Even in chlorine there are 3 shells. That means when I'm moving from left to right in the same period, the number of shells remains the same. The number of shells remains the same. And since the number of shells has remained the same, I cannot say that the one having a larger number of shells will have a larger size. I cannot say that because both have the same number of shells. So in that case, I'll compare the nuclear charge. Let's compare the nuclear charge of sodium. 11 is the atomic number of sodium. That means there are 11 protons. There are 11 protons in sodium. The atomic number of chlorine is 17. So that means there are 17 protons in chlorine. Obviously, if you see 17 protons means the nuclear charge is greater in case of chlorine. In case of chlorine, the number of protons is higher, and so the nuclear charge is also higher, as a result of which the pull will be also higher and the size will decrease. So chlorine will be smaller than sodium. So from sodium till chlorine, if I go, I'll say that the size is decreasing. From sodium to magnesium, the size decreases. Again, from magnesium to aluminum, the size decreases. Again, from aluminum to silicon, the size decreases. Again, from silicon to phosphorus, the size decreases, and so on till that point I reach chlorine. So from sodium till chlorine, I can say that the size goes on decreasing because the nuclear charge goes on increasing. The nuclear pull also increases. So within the same period, from left to right, the size of an element decreases. Now, talking about an inert gas in the same period. Talking about an inert gas in the same period. For example, if I'm talking about period 3, then argon is the inert gas in period 3. That is, after chlorine, I have argon. Now, argon is an inert gas. Just remember this. As of now, just treat it as an exception that within the same period, the inert gas has a very large size. That means if I am moving from sodium till argon, the size will decrease from sodium till chlorine, as discussed just now. Right? So from sodium till chlorine, the size will decrease. But from chlorine till argon, the size will increase. So I write here what is happening. On moving from the element present present. So what is group 17? All halogens come under group 17. That means your fluorine, chlorine, all these things. So from chlorine, if I move towards argon, that means I'm moving from Cl to Ar. So what is chlorine? Chlorine is a halogen. Why is it a halogen? Because it is present in group 17. Any element which is in group 17 is called a halogen. So I can say that from the halogen, if I move to the inert gas, so on moving from the halogen, on moving from the halogen to the inert gas, on moving from the halogen to the inert gas in the same period, the size increases. So this is one important point that you have to remember. So there is some other reason behind this. So when you are going from the halogen to the inert gas in the same period, the size increases. So this is one thing that you have to keep in mind. Next, on moving on moving down a group, on moving down a group, the size increases as the number of shells increases. As I said, more the number of shells, more is the size. So this is an important parameter. So we have discussed size. Next, after size, let's go to the metallic character. Metallic character. So here we'll say that more the tendency of an element to lose electrons, more the tendency of an element to lose electrons, higher is its metallic character. So any element which is readily able to lose electrons is like a metal, is a more metallic by nature. So more the tendency of an element to lose electrons, higher is its metallic nature. On moving on moving from left to right in a period, the metallic nature decreases. Now, why does it happen? So, if I'm talking about a period, for example, if I'm having here, let's say again sodium, and here again I have chlorine. So this is sodium and this is chlorine. Let's look at the number of valence electrons. Here sodium has only one valence electron, so it can easily lose that electron. But if you look at chlorine, chlorine has seven valence electrons. So chlorine cannot lose electrons that easily. Rather, it can accept one electron in order to complete its octet. That is, if it accepts one electron, then the last shell will have eight electrons. So rather than losing electrons, it would try to gain an electron. But in case of sodium, it is much easier to lose the electron that is present in the last shell because there is only one valence electron. If we have one or two or three valence electrons, then it is very easy for the element to lose electrons. But if an element has six, seven, eight valence electrons, then it cannot lose electrons easily. And so we say that any element which is lying towards the right hand side will be like a non-metal because it has more number of valence electrons. And any element which is lying on the left hand side of the periodic table will have less number of electrons and so it will be metallic. So towards the left we have metals because they have less number of valence electrons. And towards the right hand side of the periodic table we have non-metals because they have more number of valence electrons. So with the help of sodium and chlorine we can understand all these differences. Now we discussed the case on moving from left to right. Okay. What about going from top to bottom? Now see, if I'm moving from top to bottom, if I'm moving from top to bottom, what is happening? On moving from top to bottom, the size is increasing, right? Because the number of shells is increasing. So if I have, let's say, two shells, right? If I have two shells, then I have three shells, then I have four shells, and so on going from top to bottom. Then the last electron is becoming further from the nucleus. The distance between the nucleus and the last electron is increasing with the increase in the number of shells. So more the number of shells, more is the distance between the nucleus and the last electron present. So obviously if the distance between nucleus and the last electron present increases, if this is my nucleus and this is the last electron, then the distance is large. Since the distance between the two is large, the nuclear pull will be less because the distance is large and so the nucleus will not be able to effectively pull the last electron towards itself. If it is not able to exert its force or pull on the last electron, definitely the last electron is free and it can move out easily. That is, it can be lost by the element easily. So I can say that if the number of shells increases, it is becoming easier for the element to lose the last electron. If it is becoming easier for the element to lose the last electron, that means it is becoming more and more metallic by nature. So I can say that on going from top to bottom in a group, the metallic character increases. So on moving from top to bottom, on moving from top to bottom in a group. The metallic character increases so on moving from top to bottom in a group, the metallic character increases by due to an increase in the number of shells. So if there is an increase in the number of shells, the valence electron can be easily lost because the nucleus will become further away from the valence electron. So if it is very far from the valence electron, it will not be able to exert its force or influence to that extent. So metallic character is decreasing from left to right and it is increasing from top to bottom. So just remember, if anything increases in a period, that is from left to right, then that particular parameter will decrease down the group. And anything which decreases from left to right will increase from top to bottom. So you can just remember one, the other will be opposite. So from left to right, if I'm going and something is increasing, that the same thing, then the same thing will decrease if I am moving from top to bottom. Similarly, if from left to right I'm going and a particular thing is decreasing, then the same thing will increase when I'm going from top to bottom in the group. So the trend is exactly opposite. Whatever trend is followed in the period on moving from left to right is exactly opposite to what is followed on moving from top to bottom. So metallic character we did. Next is next trend. Next trend. Ionization energy or ionization potential. Either you call it ionization energy or you call it ionization potential. Now this, what is this? The energy required the energy required to pull out or remove the energy required to pull out or remove one electron, one electron from the valence shell, from the valence shell of a neutral gaseous atom is called ionization energy. If an element, if an element is able to lose an electron easily, then its ionization energy will be low. Means what? Means if I have to remove one electron from an element, I supply some energy. That is called ionization energy. But if it is able to lose the electron easily, that means if I am able to supply only a small amount of energy to take out the electron, that means I have to spend less energy. That means I'll have to supply less energy. Why? Because the element is ready to lose its electron. I don't have to spend a lot of energy or a lot of efforts to take out the electron. So the ionization energy will be low if the element is able to lose its electron easily. So if an element is able to lose an electron easily, then its ionization energy will be low. So on moving from left to right in a period, so what is happening from left to right? The, the metallic character decreases. Just now we learned. So if the metallic character is decreasing, that means it will be difficult for the element to lose electron because metals are very good at losing electrons. So if the metallic character decreases, that means it will be very difficult for the element to lose electron, which means that I have to supply a lot of energy in order to take out one electron. That means the ionization energy will be high. So on moving from left to right in a period, the ionization energy increases. On moving from left to right in a period, the ionization energy increases. By as the nuclear charge increases, as the nuclear charge increases, and thus it becomes difficult to remove one electron. from the atom. On moving down the group, the ionization energy decreases because now the metallic character is increasing, so it will be easier to take out electrons because the valence electron is very far from the nucleus. Why is it far? It is far because the number of shells is increasing. So if it is very far from the nucleus, I'll have to supply less energy in order to take it out. So the ionization energy will decrease if I am moving down the group. I'm moving down the group, ionization energy decreases as the size as the size keeps increasing. Due to an increase in number of shells. So this is about ionization energy. Or called ionization potential. Sometimes in the exam we just write IE or they can also write IP. So don't get confused. IP also means the same. IE or IP. You can write any of these. Fourth one. Fourth one is this. Electron affinity. Also called EA. Also called EA. So the definition for this is the amount of energy the amount of energy released. The amount of energy released when an electron is added the amount of energy released when an electron is added to a neutral gaseous atom. So when you are adding one electron to an atom, that is some energy is released at time. That energy which is released is called the electron affinity. The amount of energy released when one electron is added to a neutral gaseous atom is called electron affinity. So I can say that more the tendency, more the tendency of an atom to accept an electron, more the tendency of an atom to accept an electron, higher would be the electron affinity. So if an element is ready or it is very happy after accepting one electron, then I can say that more amount of energy will be released. So the energy released. Higher would be the energy released means it is happy after accepting one electron. And so higher is the electron affinity. Okay. So on going from left to right in a period, I'm going from left to right in the period. That means I'm going from left to right, which means I'm traveling in a horizontal manner. And as we have discussed before that, if we are traveling from left to right, the metallic character decreases. So if the metallic character is decreasing, that means the tendency of an element to lose electrons is decreasing because metals are easily able to lose electrons. So if the metallic character is decreasing, then definitely the tendency to lose electrons is decreasing. And in other words, I can say that the tendency to accept electrons is increasing. So if an element is ready to accept electrons, its electron affinity will be high, right? So if the element is happy after accepting electron, its electron affinity will be high. Usually non-metals are happy after accepting electrons, because metals lose electrons, they don't gain electrons. So if metal is able to lose electron easily, that means its electron affinity is not high because it is not happy after accepting electron. Rather, it wants to lose electron because it's a metal. But if I'm talking about a non-metal, so the non-metal will be happy if it accepts an electron, and so its electron affinity is going to be high. That means on going from left to right in a period, because the metallic character decreases, I can see that the tendency to gain electrons increases. So the electron affinity will increase from left to right. The electron affinity on going from left to right in a period, the electron affinity increases. So on going from left to right, electron affinity increases. This happens because this happens because on moving from top to bottom in a group, on moving from top to bottom in a group, the electron affinity decreases. As the size as well as metallic character increase. On moving down the group. This was about electron affinity. So what is it? It is basically the energy, amount of energy which is released when one electron is added to an atom. Next one, electron, electronegativity now. Electronegativity. It is denoted by En. Now what is electronegativity? So electronegativity is nothing but it is a it is the tendency of an atom to pull electron towards itself present in a bond. That means when a bond is formed between two atoms, Inside that bond, there are electrons present. Towards which atom are the electrons more close? That is called electronegativity. So I can say that the tendency of an atom, the tendency of an atom to pull a shared pair, to pull a shared pair of electrons, shared pair of electrons towards itself. This shared pair of electrons is where this shared pair of electrons is in the form of a bond between two atoms. So in a bond. So the tendency of an atom to pull a shared pair of electrons in a bond towards itself is called electronegativity. Non-metals are more electronegative.
So,
Yes.
actually, when I was doing a question paper, sir, I have a doubt in one question, sir.
Hmm. After this, you tell me. Let me finish this call.
Okay, sir.
So in general, non-metals are more electronegative than metals. So I can say on moving across a period, on moving from left to right, on moving from left to right in a period, the electronegativity will increase because there are more non-metals towards the right hand side. So the electronegativity will increase. Now, these are the general trends. In the exam, if they ask you to write short notes on trend, then you have to follow these that I have written. They may ask you a question like this: write about trend in electronegativity, or write about trend in electromagnetic, or write about trend in electroaffinity. So if they ask you to write short notes, then you will have to write. Now, apart from that, some other types of exceptions, or I can say exceptions, exceptions, and okay, exceptions. Let's say exceptions. Okay, exceptions or anomalies. Number one. Number one is, so they may ask you some exceptions. In case they ask, we should be able to talk about the exceptions. So first exception. First exception is this. What else? The IE. IE is what? Ionization energy. Or IP. The IE or IP of higher similarly next exception. Certain exceptions after the ones that I'm writing. Okay, this is the last part. Isoelectronic species. The species having same number of electrons. Questions are asked on this portion, so we'll do one example. Okay, example. First, let's say I have these sodium plus magnesium 2 plus aluminum 3 plus. Let's say I have these. So if I write here Na plus Mg2 plus L3 plus. Okay, I'm making columns. Let's say I'm writing here Na plus Mg2 plus and L3 plus. Electrons or number of electrons. And here I'm writing number of protons. So let's calculate number of electrons. Now atomic number of sodium is 11. So the number of protons is going to be 11. So atomic number tells you the number of protons. So 11 is the number of protons. And also 11 is the number of electrons present in a sodium atom. But this is not a sodium atom. You can see that this is sodium ion because it has acquired a plus 1 charge. Since it has acquired a plus 1 charge, it means that It has lost one electron. So the number of electrons becomes equal to 11 minus 1. What is 11? 11 is the number of electrons initially. But once it loses one electron, it will be left with 10 electrons. Similarly, for magnesium, there are 12 electrons and 12 protons in magnesium atom. But once it has lost 2 electrons because it is Mg2 plus, that means I have to subtract 2 from 12 and now it is left with 10 electrons. For aluminium, initially there were 13 electrons, but because it is Al3 plus, that means it has lost 3 electrons and now it is left with 10 electrons. The number of protons remains the same. The number of protons does not change with formation of any ion, so it remains the same. Now, the number of electrons is 10 in Na plus, it is 10 in Mg2 plus, and also it is 10 in Al3 plus. So I can say that Na plus, Mg2 plus, and Al3 plus are isoelectronic species. Since each of the above that is Na plus, Mg2 plus, and Al3 plus. Since each of the above has the same number of electrons, so Na plus, Mg2 plus, and Al3 plus are isoelectronic. They are isoelectronic. Alright. Now, what will be the order of their sizes? I have told you here electronic species proportional to their nuclear charges. That means if the number of protons is high, the size will be small. I repeat, if the number of protons is high, the size will be small because it's inversely proportional, right? So more the number of protons, smaller is the size. So let's follow that. So size is inversely proportional to number of protons. That means what? More the number of protons, smaller would be the size. Now, number of protons is maximum in Al3 plus. Since number of protons is maximum in Al3 plus, that is 13 protons are there. That means its size will be the smallest out of these three. So order of sizes will be, so the smallest will be that species which has the largest number of protons. The largest number of protons here is for Al3 plus. So Al3 plus will be the smallest of all, followed by Mg2 plus followed by Na plus. So this will be the order of sizes. Or I can write the same thing in this way. If I want to write it in descending order, this is ascending order. So if I want to write it in descending order, then the largest will be Na plus, then Mg2 plus, and the smallest will be L3 plus. So I can write in any way. That means the point is that if I have isoelectronic species, the size will be inversely proportional to the number of protons. Smaller the size means what? More is the number of protons. Okay. Now somebody had a doubt. So you can ask the doubt now. Yes? Somebody had a doubt?
No, sir.
No, one person had a doubt in some question. He said that he had to ask one
So I
question.
have one doubt. I've messaged him
So,
in the chat.
sir, I too.
So what are the doubts? Now you can ask those doubts.
So I had a doubt. So the question is state the meaning of functional group in a carbon compound. Write the functional group